All right, the next example, example 4, we're going to go ahead and take a look at, or it's a instance of what is being described here in remark 3, which is a different notation for a vector line integral. So in general, let's take a closer look at this alternate notation. Here, if you have a vector field f, whose components are just f1, f2, f3, where these f1, 2, and 3 are just functions of x, y, and z, then you can write this in an expanded form like this. Whatever's next to the dx, that tells us what the x component is. Whatever's next to dy, that's the y component. Whatever's next to dz, that's the z component. I wouldn't worry so much about this side. It's a natural extension of this. But let's go ahead and start looking at this in an example to see how it works. So in example 4, we're given the vector line integral written or given to us in this alternate format. So I do think it's worthwhile to be able to see how the two are equivalent. So note here that this line integral, 2y dx minus 3dy, this is exactly the same thing as if we had written 2y comma negative 3 dot dr. They're identical. So I'll just say equivalent. Okay, but I don't want to compute it this way. I want to get some practice with this way. So let's go ahead and take a look at that. And what I'm going to do, because I think it's very important, is if we take a look at our parameterization tells us exactly what x and y are. So we know that for our parameterization, that x is equal to 5 plus 4 cosine theta, and y is equal to 3 plus 2 sine of theta. So we can go ahead and actually replace some stuff in. So let's go ahead and erase that. And look here. Well, we know our range for t is 0 to 2 pi, so let's go ahead and fill that in. 2 times y, well, we know from our parameterization that's y. So this will be 3 plus 2 sine theta. And then we have to multiply by dx. Well, we don't have dx written down, but we can very quickly figure out dx from our x equation just by finding the differential via differentiation. So this would be dx equals minus 4 sine theta d theta. And while we're at it, let's figure out dy. dy is 2 cosine theta d theta. So we have negative 3, jumping ahead. We should multiply by negative 4 sine of theta d theta minus 3 times dy, which is 2 cosine theta d theta. We can continue here by factoring out the d theta. And if we collect terms, we should be left over with negative 24 sine theta minus 16 sine squared theta minus 6 cosine theta d theta. To do this integral here, the only part that's going to give us a little bit of trouble, or confusion maybe, is what to do with this sine squared. It's not going to be a u sub. All we need to do is rewrite sine squared in terms of an identity. This will be the half angle identity. So sine squared of theta is 1 minus the cosine of double that, so 2 theta, all over 2. If you go ahead and rewrite that, it's a very straightforward integral, and the answer is negative 16 pi. So people do like this notation. You don't have to worry about the vector notation. Sometimes it's nicer to just work with the dx's and the dy's, but it can give some confusion because It is a vector line integral, but when you look at it, there's no vector in it, right? This notation here, there's no vectors. We know to interpret these function coefficients, f1, f2, and f3, as the components of a vector field, but within this expression, there is no literal vector. To contrast that with over here, what we learned first, there is definitely a vector there. So sometimes this notation, if you're not used to it, can throw you off into thinking that this is not a vector line integral. That's probably the most common kind of issue that we get is sometimes when an alternate notation is used, the scalar and vector line integrals, the two methods to compute them, although they're very similar, they are different, and they'll sometimes get meshed together in a less than ideal way.